what I got next, I created this slide deck last year because normally on the last day, what I did the first 2 years I taught this course was I did a building tour of our McKinstry building and actually taken you into the basement and looked at water source heat pumps and talked about all the parts and pieces that we've talked about in class, but seeing it in person is always a little different. So last year, obviously we couldn't do that because we had gone virtual for the second half of the semester. We're in the same boat now. So what I'm talking about today is some of the newer technologies or just some special topics that we didn't really cover, but that are related to energy auditing or HVAC. Just as kind of a FYI, it's pretty broad strokes, but maybe you'll find it interesting. So the first topic is what's called net zero buildings, which is it's a rising trend. It's kind of a buzzword right now that is really gaining some traction. So there is no such thing as a zero energy building. Net zero and zero energy are not the same thing. Buildings will always need to use some kind of energy. To run a pump or a fan or to do anything, we have to use energy. So zero energy, that's not the right term. But what we can do is offset our building's use through either on-site renewable generation and highly efficient HVAC systems. And I said either one of those, but really it has to be both. We have to have some sort of on-site renewables in addition to extremely efficient systems. So we could have some wind turbines or some solar PV panels, or one thing we have talked about is solar domestic hot water heaters and using the sun to heat our domestic hot water to provide that to our building. And it's difficult, maybe impossible, to completely offset that peak power draw every hour of every day. So if you did a model of your building or you looked at your utility bills and you see that, hey, my peak demand is 200 kilowatts every month, it would be very difficult to install enough renewables to completely offset that 200 kW. But what if we generate some power to offset some of that energy during the day, and then other times of the day we generate excess power, which would be during the off hours on nights and weekends, meaning we're sending energy back into the utility grid. So to visualize that, let's say we're looking at our building over a typical week. We have the power draw of our building on the y-axis, time on the x-axis, and let's say this is the general curve of the power use of that building for this given week. So we have these 5 peaks here. So that's probably our week, Monday through Friday. And you can see it ramps up in the morning to a hot day when all of our air conditioning systems are running. And then as people leave, it gets cooler outside, and then it just repeats for those 5 days. And then we have this weekend period where we still get, maybe a hump, or maybe this is just one day off, say a holiday or something. And then our week starts over again. So that would be our typical power profile. And let's say we have some on-site renewable energy generation, this green line. Let's say that's solar PV panels, meaning we get more generation at the peak of the day when the sun's nice and high, which happens to be at the same time that our air conditioning systems are peaked out. And then it drops as we get to nighttime. And so we're always just offsetting some of our energy, but not all of it. So this orange, this area in orange, that would be the amount of energy draw we would need to pull from the utility. So we would still need to be getting electricity from our utility provider. Not as much as a regular building, but we still need some. So we can't disconnect from the grid entirely. But then you notice, well, here on the weekend, our PV systems, well, they didn't reduce their output. They don't care if the building's occupied. They just care about whether the sun's out. And so now we have an inverted area here in blue, which is going to be the energy that we're sending back into the grid. So some times of the day or week, we're pulling energy, we're buying energy from the utility, and then we have these other times where we are actually selling them energy. So in that example, we're still pulling energy from the grid. But on the moderate days, maybe only on an 80-degree day or on nights and weekends, those are the times where we're going to be sending energy back. And if we can make those areas of the curves, what's drawn versus what's given back, if we can make those areas equal over a full year, which is usually how they track it, is by year, January to December, that would be considered a net zero building. Not a zero energy building, because there's still many hours there where we're in the negative and pulling energy from the utility, but maybe over a year we can even those out, make it average out so that it's zero or below zero. Usually you need to have a lot of on-site generation to do that and have super efficient systems and have the control strategies to achieve net zero. So there are some control strategies that the energy code says, well, we're not going to make you do that because it's a lot of hassle and maybe doesn't save as much energy as some of the more essential control strategies. Well, if we're trying to achieve this net zero building, we have to pull out all of the stops and save every kilowatt hour we can. The next thing is heat recovery chillers. So heat recovery chillers, these are not like energy wheels, pumped runaround coils, or fixed plate heat exchangers, which we just talked about when we were talking about energy recovery methods. These are using a DX based, so this is a refrigeration process, water to water heat exchanger. And normally, if you have hot and chilled water systems, they're entirely decoupled, which means the hot and chilled water systems are completely separate. They don't interact at all. Completely decoupled systems. The chilled water system does not care what's going on with the hot water system and vice versa. But heat recovery chillers provide hot and chilled water out of the same unit. So this is essentially a really fancy water to water heat pump. Mainly, we talked about water to air heat pumps, where we have a condenser loop and we're either pulling heat or rejecting heat into the water and either heating or cooling our air as a result. So that would be a water to air heat pump. These are water to water. So we have our warmish chilled water returning after it's served its load. And then the chiller, whose job is to chill that water down. If it's going to chill the water down, it has to get rid of that heat somewhere. And normally we reject that heat outside. In this case, we're going to reject the heat directly into the hot water stream. So standard chiller goes outside. In this case, we're putting it where it can actually be used. So now we can actually use that heat to heat up the hot water stream. And now we've helped serve the hot water load, and maybe we don't have to run the boiler as much. So it's just another idea of sharing energy. So what would that look like in practice? I realize this is a lot. There's a lot going on in this diagram, but let's walk through the primary components. We have our chilled water system. So this is pumping chilled water through some air handlers, through some chilled water coils, wherever that chilled water is needed. And then we have 3 water source chillers, and you can tell they're water source because on this side, they're connected to a condenser water system. You have your cooling tower. So as these 3 chillers are running, they're pulling heat from this side, rejecting it into the condenser water, which then goes into the cooling tower where it gets rejected outside. And then down here, we have our hot water system. So a bunch of boilers producing hot water. And then we have this 4th chiller right here, which is our heat recovery chiller. And you can see that this chiller has on one side of it chilled water in and out, and on the other side it has hot water in and out. And so this is actually going to transfer heat from the chilled water side into the hot water loop. So instead of rejecting it all at this cooling tower up here, well, let's take some of that and dump it into the hot water stream. And that way these boilers don't have to work quite as hard. And this is fairly common to have essentially a mix and match. It's not all heat recovery chillers. Usually it's, you still have the water source chillers that are serving most of the load, and then you might have 1 or 2 heat recovery chillers to take advantage of that. But it kind of depends on how much of that heat recovery benefit we can actually see. It might be overkill to have 4 heat recovery chillers here. And this is more of what the guts look like. So this would be 3, they call them modular chillers, where they basically take 3 smaller chiller modules and slap them together to make one big chiller. But in each one of those modules, you have the evaporator and the condenser. You have your hot water stream coming in on one end, your chilled water stream on the other. And so it pulls heat out of the chilled water side, goes through the evaporator. We have our DX process, and then the condenser rejects that heat into the hot water side. Now, this only works if you have heating and cooling loads simultaneously. If you have no cooling load in the winter or no heating load in the summer, where's the opportunity to share energy? If those 2 systems aren't running at the same time, then what's the purpose in sharing this energy around? And that is true with most commercial buildings. If you look at a typical school or a typical office building, this is true. There isn't a lot of opportunity there to share energy because whenever the chillers are running, the boilers are off, and vice versa. So this is going to be more applicable for buildings that have what are called process loads, which is essentially saying any loads that are non-HVAC related. So you could have a factory that needs to use hot water in its whatever machinery you're running to make whatever product you're making in there. And you might need that hot water year round, or you might need chilled water year round, even in the peak of winter, because whatever you're doing in that manufacturing plant or that lab needs chilled water all the time. So that would be a good example for when a heat recovery chiller could actually save you a lot of energy. And the savings are kind of twofold. You're saving it on the chilled water side because now you're not having to run your cooling tower to reject that heat outside, and you're not having to run your boiler as much because you're getting the heat from the chilled water side. quick slide on VRF. So VRF is considered a somewhat newer technology. It's technically been around, I think, since the late 1980s is when it first popped up. But that was over in Europe and possibly Japan, I think. Most of the VRF manufacturers are Japanese. But it took its time to get to the United States. So in the United States, it's still considered kind of a newer technology. We've already talked at length. I had a whole lecture on VRF systems, but similar idea to a heat recovery chiller. Anytime we can share energy, that's a really good thing. That's a way to operate things very efficiently. And then we have chilled beams. So what a chilled beam is essentially a chilled water cooling coil that hangs up in your ceiling. So you can imagine this sitting in the ceiling with some ceiling tiles surrounding it to give it a nice flush look. So we're going to supply a small amount of ventilation air into this unit. That would be this collar right here. So we would duct up a DOAS ventilation unit and push some ventilation into the coil right there. And that that ventilation air that's going into the unit is going in at a really high velocity, which is actually going to induce some return air into the bottom of the unit. I'll have a better image here in a second. One good thing about these is they have very low fan energy requirements, which I'll dive into in a sec. They also provide improved chiller efficiency. The reason being, with chilled beams, you need to keep your chilled water temperature higher. A typical chilled water system supplies water at right around 45 degrees Fahrenheit. The problem is, if you put 45 degree water through this coil, you're going to have that latent load. You're going to be below the dew point of the air that it's pulling in, and you're going to cause it to rain in that space. Remember that every cooling process, or most cooling processes, they produce condensate. They produce water because it's sweating it out of the air. And we don't want that to happen here. Behind this grill is a chilled water coil. And if that starts to sweat that condensate out, well, that's just going to go straight on somebody's head. So we have to keep the chilled water temperature higher, more like 55 degrees, to raise it above the dew point of the space to prevent that water from condensing. And as we know, if we have higher chilled water temperatures, that means we have lower chiller lift. The chiller compressor doesn't need to work as hard, but you have to make sure you design it for those conditions. You have to have more robust coils to get the same level of cooling with warmer water. And so these beams, they are sensible cooling only, which means the latent load that's going to be produced by all of the people that are in the space has to be picked up at the DOAS unit. So these are typically paired up with large direct outside air systems. And at those units, that's where we have to have some additional cooling to handle that latent load so that we don't end up building up humidity and moisture in the room. So this is more of a section view of what this looks like. So here's our primary air, which is coming from a DOAS unit. And then it enters this, I guess I'd call it a plenum, where it pressurizes in here as it's trying to force its way in. And then you have these nozzles, these tiny nozzles that are going to force this air to discharge at a very high velocity. And so if you're blowing this air at a very high velocity, the Coanda effect will induce some air to kind of follow suit. It'll kind of pull it along because that air is moving so fast. The adjacent air is going to kind of come along for the ride. And so as it pulls the air here, that creates a vacuum below, which then pulls air in through the bottom. So you're getting about 1 part DOAS air that you're pushing through these nozzles, and then you get 2 to 4 parts of this return air. So overall, between those two, we're still moving a fair amount of air, but there's no fan inside this chilled beam. The only fan is what's moving this single part of primary air up at your DOAS unit. And this kind of illustrates the thermal performance. So you'll have the warm air getting pulled in through the center of the coil, which then the cold air gets pulled or pushed out the edges. I haven't designed a chilled beam system yet, but they're kind of a rising technology right now. And then we have absorption chillers. And this is not a new technology. Absorption chillers have been around for a long time, but it is kind of a cool thing that we rarely see. So this is a strange beast. This is an oddball chiller. It uses a heat source to cool a water. So it's a chiller, meaning its goal is to produce chilled water. And it does that using a heat source. So that sounds a little odd. There isn't a compressor. So there's no compressor driving a refrigerant process between the evaporator and the condenser. Well, that's totally different from every other chiller. It actually uses water as its refrigerant liquid mixed with some lithium bromide or ammonia. Well, that's not like any other refrigerant we use in any other chiller or air conditioner. So everything about this just screams, what is going on with this chiller? Why is this one so different than every other chiller? Or at least why is it so different from a traditional chiller? So what's going on here? It's using a waste heat source, which forces the water, which is our refrigerant in this case, forces our water to evaporate, and then it condenses and evaporates and condenses. And it does this through some high and low pressure chambers that actually manipulate the water boiling points. So it is still a refrigerant process that we are going between a high pressure gas to a liquid, kind of back and forth, just like other refrigerant processes in air conditioning. But it's using these pressure chambers to manipulate these boiling points of the water, which normally wouldn't want to react this way. It normally wouldn't want to do these phase changes. There's way too much here to go over and explain. If you're really interested, there's a YouTube video on it. But the explain like I'm 5 oversimplification is we're going to take some heat source, and that is our input energy to drive this strange refrigerant process. And then we're going to produce some chilled water. That's our useful output. It's not very efficient, 0.7 to 1.2 COP. That's not that great. By comparison, DX chillers are right around 3 to 4 COP. So why would you ever use an absorption chiller as opposed to a standard DX chiller? Well, this makes sense if you have some waste heat to work with that's otherwise unused. If you have some heating source, let's say you have some hot water that results from some process in your factory. Whatever process you have produces this hot water, and you just dump it outside because you have no other use for it. Why do I need it? Dump it outside. Well, in that case, you're dumping a lot of energy outside because this water is really warm, and why not instead send it to an absorption chiller, assuming you need chilled water at your building as well. So this is all the parts and pieces of an absorption chiller. There's a lot going on here. This is an excerpt from that YouTube video. But what we can identify, we have our heat input. So this is our hot water, or maybe it's steam, some sort of waste heated liquid that is otherwise going to be unused. That's our input. So we're bringing in the hot water, you can see a pump there, into this generator section, which is our water and lithium bromide mix, where it heats that up and then ends up leaving. And then it does all kinds of wacky, crazy things between the condenser section up here and the evaporator section down there. I can't explain all this stuff. I've never spec'd an absorption chiller, but this kind of boggles my mind that somebody thought of this. But at the end of the day, we have a chilled water output. So we're bringing in some warmish chilled water where it gets cooled down in the evaporator and then gets sent back out to do whatever that chilled water is designed to do. And ultimately, we are still rejecting the heat outside. We still have a cooling tower to get rid of that heat from the chilled water side. We have to get rid of it somehow. It can't just stay in the chiller. The laws of thermodynamics wouldn't be too happy about that. It has to get outside somehow, and so that would be a cooling tower. And that's what a big old absorption chiller would look like. And they tend to be pretty big. I mean, if you can imagine a 6-foot person standing probably, high level with that control panel, that's a pretty big chiller. So that's it for the new technology. I got a few more slides for you if you'll bear with me. This is my good luck out there portion of the class. Just to give you one final parting set of advice, things to consider as you're going into the real world. So some real life considerations. Please don't get stuck on getting your dream job right out of college. If you can, at least get on the right track. It can be pretty hard to change later. If I entered the HVAC industry and I did it for 3 or 4 years, and then I had an epiphany and realized, man, I'm miserable, and I should have chased my dream of working on cars or whatever. That's really hard to do 4 years later. You're essentially hitting the reset button, and all of my great experience in HVAC is probably not going to translate very well to most of the other industries. Additionally, chances are extremely high that wherever you land your first job, that will not be your last job. I don't know what the average is now, but most people probably go through at least 7 or 8 jobs in their lifetime, I would guess. I've been fairly fortunate. I'm only on my 2nd, but who knows? Maybe in a few years, I'll decide that I've learned everything I can learn in this position and decide I want to spread my wings and go somewhere else for new challenges. You also likely don't really know what you want and what kind of things you enjoy doing. I have a pretty good sense now of the types of tasks I enjoy doing. I can say with confidence that I like getting into the technical aspects of engineering. I like nerding out on engineering concepts and readings of the code. That's not for everyone. I also know I don't really like managing people. And so if somebody were to offer me a managerial role, I'd probably think twice about that. But I only know that because I've been doing this long enough that I've had exposure to those various aspects of my job, and I know what I like and what I don't like. Another example, when I got out of college, I had no idea what a good benefits package was. I got my job offer, which included a benefits package that told me all about the insurance and 401k plan and all that good stuff. I didn't know what any of that meant. I was just happy to get a job. But now I have a wife and 3 kids. They're all on my insurance plan. If I were to change jobs, I would be looking extremely closely at that benefits program for whatever company I was looking to go to. That company might say, pay me an extra $10,000 in salary, but if the benefits package is not as good, maybe that 10,000 per year is not as much as I think it is. I remember there was one guy who left McKinstry and came back a couple years later, and um, the company he had gone to in the interim, they had offered him a pretty good salary, but he said the benefits was so much worse that he actually felt he had to counter offer and say, look, your benefits package is not nearly as good as the one I'm currently on. I want to be compensated more with additional salary. And they made it happen. I also have a pretty good sense of what kind of office environment is for me. If I were to interview at a new company, I would be looking around the office and trying to gauge a sense of what is that office environment like. I would probably even ask whoever I was interviewing with if I could maybe chat with one of someone who would be my peer, just to kind of get a sense of what it's like to work there. And ultimately, sometimes to really know what you don't want, you have to experience it first. I mentioned this before. Don't be afraid to ask questions, and don't ascend to the peak of Mount Stupid. Back when we talked about the Dunning-Kruger effect. So you better ask your dumb questions now, or you will stay dumb forever. This was a big one for me. My first boss right out of school, he seemed to think that I should know a lot more about HVAC than I did. And that caused a lot of anxiety and second guessing in myself and my abilities, to the point that I kind of shut down a little bit and just didn't ask questions. And that's the wrong move. So today, thankfully, when I came to McKinstry, I found much better mentors who made it very clear early on that I don't care if you're a senior engineer, you ask those dumb questions. It's okay to ask dumb questions. This is a quote I like to say. It's okay to not know things. I don't know who's that's attributed to, so I threw Abraham Lincoln on there. It's okay to not know things and ask questions. And just because you work with somebody who makes you feel like it's not okay, that's not on you. Speaking of postgraduate education, I'd recommend waiting a little bit. I'd say wait until you get some experience in whatever field you want to go into, unless you are going a very specific path, like the one of you who's going into law school. I suspect you have a very specific plan in mind on where you're going with that. But if you are getting an MBA or something like that, I'd say wait until you have some experience. And ideally, your employer might help pay for that. Maybe not all of it, but they might help pay for at least some of it. So if you're thinking about postgraduate education down the road, have a goal in mind. Don't just go get an MBA because you don't know what else to do with your life. Why not? I'll go get my MBA. That's not a good reason to do it. There are many good reasons why you might want an MBA, but have some kind of goal formulated in your head. Not only that, these master's degrees cost a lot of money. And if you have some experience in whatever industry you're in, whatever knowledge you're getting in this master's program gives you some context. So again, with the MBA example, MBA programs are all about business. Well, if you've been working for a company for 3 to 4 years, you've gotten a glimpse of how this business operates. Hopefully, you're asking questions about how do we make money? Don't just take the task given to you, ask those kinds of questions. Ask about the business side of things. And now, as you're learning this new knowledge in your master's program, you actually have something to apply that to. And I think that's going to make that program a lot more valuable for you. And it may take some time to feel like you're part of the team. I remember coming into my first job or my second job as well, and it feels like you're walking into a group of friends who have all been friends forever and they all have inside jokes, and you don't understand any of those inside jokes, and you just feel like an outsider. So that was a big hurdle for me. I just didn't really feel like I belonged with this company as part of this team. Some of that probably has to do with some of my own anxiety issues I was dealing with at the time, but it took a long time to feel like I was actually a part of that team and actually producing something useful as part of that team. Ask for feedback. How am I doing? What can I do better? What are resources I can use to improve myself? Some companies have very formalized annual review processes. Like McKinstry, I have to meet with my boss. I think we meet quarterly, and I have a set of goals every year that I'm trying to hit. And it is kind of frustrating and it seems kind of arbitrary, some of the goals that are listed there. But it is important to at least get some feedback from your boss, to just ask them, how am I doing? What can I do better? The companies that don't have those formal processes, they're probably not going to tell you anything unless you ask the question directly. Always push yourself to learn new things. The more hats you can wear, the more valuable of an employee you are. So get comfortable being uncomfortable. If you can develop those related skill sets, that makes you a better engineer. Within McKinstry, I have I've worn many different hats. I've been part of different teams. When I've gotten slow in my primary duties, I've run out of stuff to do, I go talk to somebody in a different department and say, hey, yeah, I'm looking pretty light the next 2 weeks. I was wondering if I can help you with anything. And then by learning those skills, that helps you get in the mindset of what someone in those other roles might be thinking. So now I know more about what our construction team is thinking. As I'm doing my design, I can start to think, not just like an engineer, but I can think about the people who are going to take my drawings and actually have to take those lines and circles on the paper and turn it into something real. Don't be afraid to own up to your mistakes. Hopefully it wasn't something really bad, or it's something that just keeps happening over and over again. I really hope you learn from your mistakes. But if you own up to your mistakes, that should boost your credibility. The team should trust you a little bit more if you're willing to own up to your mistakes. Don't throw anyone else under the bus. Don't try to hide it. Everyone makes mistakes. Everyone's human, but do your best to be active in finding a solution. But also, if your boss, if you find that they're holding this kind of stuff over your head and they just don't let you forget about this mistake you made, months ago or years ago, that could be a sign of a toxic work environment. A good work environment, a good manager should recognize that mistakes happen and that it's okay. Last slide. Don't be afraid to push back if you're not comfortable. If somebody gives you a task and you're just, a little uncomfortable with what they're asking you to do because you don't know how to do that task. And you can phrase that as, I just want to make sure I get this right. It's okay to push back. Just be respectful about it, I guess. Because ultimately, it is much better to do something completely correct with a little bit of hand-holding rather than screw something up that costs you a ton of money down the road. We've seen this happen in construction projects a lot, where somebody makes a mistake, or maybe they didn't know what they were doing, and then during construction, which can be months later, at that point it could be too late, because we've already ordered all of our equipment and we can't just call the manufacturer and say, oh no, this isn't what we wanted, we needed this other thing. It's not that easy. It's super important to get it right at the beginning. So don't put something on paper that you think might be right and assume whoever's reviewing your work is going to catch it. Because I've seen reviewing engineers miss all kinds of stuff. They're not necessarily looking through your work with a fine-tooth comb, and they are going to miss things. So if you are wondering if, well, maybe I didn't do this right, bring it to their attention, or maybe when you give it to them, you flag it in some way. Mark it up on the PDF, put a box around it with a note that says, hey, I don't know if I did this right, so I really want to make sure you catch this. And a big one, find a mentor. Find a good mentor, not a bad one. I mentioned my first mentor was not the best. Nice guy, just not a great mentor. But find somebody in the company that is who you want to be, and then just be like them. Try to be their shadow, do things the way they do it. Just be a sponge and learn everything you can from that mentor. And that's it for this class. Any parting comments, questions, thoughts, complaints? All right. Well, we got 20 minutes. If there's any final homework questions, I'll stick around. Otherwise, it's been a pleasure, and I will see you all Monday.
Thank you.
Thank you.
Thank you.
Thanks. It's been a great class.